let's review strong acids and bases. The 7 strong acids and 8 strong bases exist entirely as ions in aqueous solution. From this slide, what we need to know are what I call the 7 strong anions, which are the anions of the 7 strong acids, and we need to know the 8 what I call strong base cations, which make a little lowercase b right here. If you have a good imagination, you can see this thing that I've colored in black here. It's like a lowercase b. Those are what I call strong base cations. We need to know the 15 strongs that are shown on this slide. To predict the pH of a salt solution, look at the formula of the salt. For salts with ions related to a strong base and a weak acid, for example, NaClO, Na is related to the strong base NaOH, ClO is related to the weak acid hypochlorous acid. Here's another example. The cation is related to a strong base, the anion is related to a weak acid. Strong base, weak acid, we predict a pH greater than 7. In other words, in the basic region. What if we have a salt that has ions related to a weak base and a strong acid? For example, ammonium chloride. The ammonium ion is related to the weak base ammonia, and the chloride ion is related to the strong acid, HCl. Similarly, aluminum hydroxide, we would have to consider that a weak base. It's certainly not a strong base. And then the nitrate ion is related to the strong acid, nitric acid. In these cases, we have ions related to a weak base and a strong acid. Weak base, strong acid. You would think the acid would win, and the pH would be less than 7. What if you have ions in the salt that are related to a strong base and a strong acid? You can see in these two examples, the cations are related to strong bases, and the anions are related to strong acids. And in this case, we predict a pH equal to 7. It's a tie. And finally, what if the ions in your salt are derived or related to a weak base and a weak acid? This one we can't tell by inspection. We have to actually do a little work for this, but here's what you would do. You would compare the Ka for the cation with the Kb for the anion, and the pH goes the way of the larger. Here is a salt that is derived from a weak base, ammonia, and a weak acid, acetic acid. What we would need to do, and this might require a calculation or two, we would calculate the Ka for the ammonium ion acting as an acid, and the Kb for the acetate ion acting as a base, and whichever one of those is bigger, that's the way the pH is going to fall. If we had another example, this is ammonium cyanide. We would need to find the Ka for the ammonium ion versus the Kb for the cyanide ion, and whoever's bigger wins. Notice that we only need to do this. We only need to work when both of the ions are related to weaks. Let's summarize the shortcut for predicting the pH of salt solutions. 1. Look at the salt's formula. Decide if the salt's cation is related to a strong or weak base. Also decide if the salt's anion is related to a strong or weak acid. Number 2 is 2 sentences in one. I'm going to read it first using the boldface terms, and then again using the underlined terms. If the cation is strong and the anion weak, the solution will have a pH greater than 7. If the cation is weak and the anion strong, the solution will have a pH less than 7. 3. If both ions are strong, pH equals 7. If both are weak, compare the cation's Ka with the anion's Kb. pH goes the way of the larger. 4. Let us stress that The reason a salt solution has a given pH is due to the activity of the weak ion, which accepts or donates protons. Strong ions do not affect pH. The nitrate ion, for example, will not accept protons. So, the reason that a salt solution has a certain pH, ironically, is due not to what I've called the strong ions, but to the effect of the weak ions.